Hello everyone, I'm Dr. Vandana Masi, Assistant Professor of Physics in KIET Group of Institutions, Ghaziabad. In today's lecture, we'll talk more about diffraction at single slit. The contents of this lecture are theory of diffraction at single slit, then intensity distribution due to single slit, spread of central diffraction maximum, and thereafter numericals to understand things better. Now we consider a narrow slit AB and the width of this slit is taken to be small e. Light is falling normally on this slit, and after diffraction from the slit, light is focused on screen SS' as you see in the figure. The focusing is done due to convex lens capital L, and here light which falls on the slit has wavelength lambda. Now according to Huygens principle, every point of the wavefront in the plane of the slit is a source of secondary wavelets. These wavelets travel towards the screen SS' and here the wavelets which travel normally to the slit, they are focused at point P0, and the ones which are diffracted at an angle theta with respect to the horizontal are focused at point P1. We have to find out the intensity at point P1. And we all know that this intensity depends upon the path difference between the secondary wavelets. In order to find out the path difference, we shall draw a perpendicular from point A to BR, and this perpendicular meets BR at point C. The path difference, as you see, is BC, which we denote by delta. Simple trigonometry can show that BC is equal to AB sine theta, but AB we've considered as E, so this becomes E sine theta. The path difference here is E sine theta, and therefore the phase difference, which is equal to 2 pi upon lambda into path difference, is equal to 2 pi upon lambda into E sine theta. We now divide this slit AB into n equal parts. I repeat, equal parts. And because we've divided this into equal parts, the amplitude of each part is equal, and let us say it is A. And the phase difference between any two consecutive wavelets which emerge from any two consecutive parts is the total phase difference divided by the number of parts we've divided the slit into, and that is n. So the phase difference between any two consecutive wavelets, which here we consider to be emerging out from the center of each part, is delta, and that is equal to 1 upon n, 2 pi upon lambda, E sine theta. Now we have to find out the resultant intensity at point P1. In order to find out the intensity, we shall first find out the resultant amplitude at point P1. And for that, we use resultant of n simple harmonic motions, which we have studied in a previous lecture. Now we all know that resultant of n simple harmonic motions with resultant amplitude A and equal phase difference between consecutive simple harmonic motions is given by R equals to A sine n delta by 2 upon sine delta by 2. And if here we substitute the delta for our condition, that is diffraction at single slit, we get R is equal to A sine alpha upon n. Here alpha is equal to pi upon lambda E sine theta. This value of alpha is important. We shall consider it many times in our further calculations. Now n is a very large number, and therefore alpha upon n is a very small value. And because alpha upon n is a small value, so sine alpha upon n, it tends to alpha upon n. As you know, sine of a very small angle tends to the angle itself. So now we get R is equal to Na sine alpha upon alpha, and Na we take as capital A. Therefore, R becomes capital A sine alpha upon alpha, and therefore the intensity at point P1, which can be found out by squaring capital R, becomes A square sine square alpha upon alpha square. So intensity is A square sine square alpha upon alpha square. Intensity distribution due to single slit. We now have to analyze the different intensity conditions. So the first one that we consider is principal maximum. It is also called central maximum. Equation 5 will take maximum values for alpha equals to 0. Alpha equals to 0 simply implies that pi upon lambda E sine theta is equal to 0, or sine theta is equal to 0 and theta is equal to 0. So this is the condition of principal maximum, and it clearly states that since theta is equal to 0, principal maximum or central maximum is formed at point P0 on the screen. Now we have to find out the intensity of principal maximum. For this, we substitute the condition of principal maximum in equation 5, but that will give us 0 upon 0, which is the undefined form. Therefore, even before we put the condition of principal maximum in equation 5, we shall expand sine square alpha. So what do we do? The intensity of principal maxima I0 for us now is equal to limit alpha tends to 0 r square, which is equal to limit alpha tends to 0. I shall put the value of r square, which is a square sine square alpha upon alpha square. Now this is equal to limit alpha tends to 0 a square, and now over here I will expand sine square alpha. So I will get alpha minus alpha cube upon factorial 3 plus alpha to the power 5 upon factorial 5 and so on whole square upon alpha square. Now if you take out alpha common in the numerator, the alpha square in the numerator will cancel the alpha square in the denominator, and we shall be left with a square. We shall now find out the conditions of secondary maxima. In order to do that, we shall differentiate equation 5 with respect to alpha and then equate it to 0. So we get di by d alpha is equal to a square 2 sine alpha upon alpha, alpha cos alpha minus sine alpha upon alpha square equals to 0. So from here we get that either sine alpha is equal to 0 or alpha cos alpha minus sine alpha is equal to 0. But sine alpha equals to 0 is the condition of minimum, so we cannot consider it here. And therefore, the condition of secondary maxima becomes alpha cos alpha minus sine alpha is equal to 0, or alpha is equal to tan alpha. Now we have to find out the values of alpha which satisfy this equation, and we do that graphically. Now in this equation, if I put alpha equals to y, I get tan alpha is also equal to y. So we'll be plotting the curves y is equal to alpha and y is equal to tan alpha. Now if you see from the figure here, y equals to alpha is a straight line which passes through origin, and it makes an angle of 45 degrees with the horizontal. And y equals to tan alpha is a discontinuous curve which has a number of branches with asymptotes at intervals alpha equals to pi. The points of intersection of the two curves give the values of alpha. The points of intersection which give secondary maxima are alpha equals to plus minus 3 pi by 2 plus minus 5 pi by 2, and similarly if we generalize this we get 2n plus 1 upon 2 pi. So alpha becomes plus minus 2n plus 1 pi by 2. Here n can take values 1, 2, 3, so on and so forth. Now if I put the value of alpha and solve it, we'll be getting pi upon lambda e sine theta is equal to plus minus 2n plus 1 pi by 2, or E sine theta is equal to plus minus 2n plus 1 lambda by 2. Here n is equal to 1, 2, 3, so on and so forth. The point of intersection, that is alpha equals to 0, is not taken because that is the condition of central or principal maximum. Now we can find out the intensities of various secondary maxima simply by substituting the value of alpha for secondary maxima that we just obtained in equation 5. Let us find out the intensity of first secondary maxima, which we denote by I1. So this I1 becomes a square sine 3 pi by 2 upon 3 pi by 2 whole square, which is equal to 4 upon 9 pi square a square, which is equal to a square upon 22. Since a square is the intensity of central maximum, we can write that as I naught. So I1 becomes I naught upon 22. Now if I solve 1 upon 22, it can be written as 4.5 upon 100 or 4.5%. So I1 is 4.5% of I naught. So we get I1 upon I naught is equal to 4 upon 9 pi square, which is equal to 1 upon 22. Similarly, since the value of alpha for second secondary maxima is plus minus 5 pi by 2, we can find out the intensity of second secondary maxima, which we denote by I2, and it is a square sine 5 pi by 2 upon 5 pi by 2 whole square. Now this is equal to 4 upon 25 pi square a square, which is equal to a square upon 62, which is equal to I naught upon 62. Again, 1 upon 62 can be written as 1.61 upon 100 or 1.61%. So I2 is equal to 1.61% of I naught. You can also write this as I2 upon I naught is equal to 4 upon 25 pi square, or simply 1 upon 62. And similarly, you can find out the intensity of any secondary maxima that you wish to. So now we see the relative intensities of central maxima, first secondary maxima, second secondary maxima, third secondary maxima, and so on. And they are in the ratios 1 is to 4 upon 9 pi square, is to 4 upon 25 pi square, is to 4 upon 49 pi square. And if we try and plot the intensity distribution graph for diffraction at single slit, the graph that you get is what you see in the picture here. Over here you see that right at the center you get the principal or the central maximum, as you call it, and it is over here that most of the light is concentrated. Then on both the sides of this you see the secondary maxima, and their intensities are falling rapidly. And in between any maxima you see the minima. We now study the spread of central diffraction maximum or principal maximum. From what we have studied so far, we know that the central maximum lies between the first minima on both the sides. The direction of the first minima is given by the equation E sine theta is equal to plus minus lambda. Remember, we are taking the first minima, so n is equal to 1. Now solving this, we get sine theta is equal to plus minus lambda upon E, or theta is equal to sine inverse plus minus lambda upon E. So central maxima extends between theta equals to sine inverse plus lambda upon E and theta equals to sine inverse minus lambda upon E. So the total angular width of central maxima is 2 theta. This is the angle when measured in terms of theta, or the angle. If the position of first minima measured from the center of the screen is y, then the linear width of the central maxima is 2y. If theta is small, sine theta tends to 0, and this is what happens in all the cases. the direction of first minima given by E sine theta equals to plus minus lambda can be easily written as E theta equals to plus minus lambda, or theta becomes lambda upon E. Now from the single slit ray diagram that you saw right at the beginning of this discussion, it can be easily seen that theta is equal to y upon d. Here capital D is the distance between the slit and the screen. So y becomes theta into d, or 2y becomes 2 theta into d. So we can say that linear width of principal maxima is equal to angular width of principal maxima into the distance between the slit and the screen. You also have to remember that y is called the half linear width of principal maxima and theta is called the half angular width of principal maximum. Now a numerical to make things a little easier to understand. The question says that a monochromatic light of wavelength 6000 angstrom passes through the single slit. It produces the first minima at 30 degrees in the diffraction pattern. Determine the slit width. So here we have to find out the width of the slit. Now we know that for minima due to single slit, the equation is E sine theta is equal to m lambda, where m can take integral values 1, 2, 3, so on and so forth. Now what is given to us is lambda is equal to 5000 angstrom, or 5000 into 10 to the power minus 10 meters. Theta is equal to 30 degrees. So for the first minima, m is equal to 1. And substituting all these values in the condition or equation for minima, we get E is equal to 12,000 angstrom. This is all for diffraction at single slit. Thank you for attending this lecture. I will see you in the next lecture.